And then the next one, I just quickly wanted to go with the analytical methodologies. And I don't want to go into too much of the mathematics because it can get a little complicated here. But what is done in the CPC methodology, this is the traditional one that was done back in 2005, is you're taking the RRI data from either EKG or PPG, and then you're doing the respiration data, again derived from the EKG. And then you're taking a window of about 1,024 samples at 2 hertz sampling frequency, right? Which equates to about 8.2 minutes. And what you do is you divide this window into 3 sub windows, each about 512 samples long or 4.1 minutes. And to each of the sub windows, you calculate the Fourier transform to both the RRI data and the respiration data. You calculate the cross spectral power. So this calculates the amplitude for each of the frequency components. And then that also creates the phase difference between the respiratory and cardiac components. And then you apply these 3 measures and apply it to the full window and to calculate the coherence. So what that means is that, so let's just say the the heart rate and respiration has a lag of, let's say 180 degrees in one window. You wanted to see whether this lag in phase is the same for across the 3 windows. If it is the same, this coherence value becomes 1. If it's not the same, like if it's 180, 90, 0, then it becomes close to 0. And then you calculate the CPC. So this one calculates the phase coherence. This is the amplitude. And then you get the CPC. And then you shift the window by 2.1 minutes, and then you repeat it. And that's how you get the values that you get on the CPC reports. What are the limitations to this traditional CPC method? Now, this CPC method, ever since the 2005, has basically not changed. It's been the same method, and it's one that's repeatedly been used in subsequent publications. And it's interesting that it sort of relies on the Fourier transform. There are many new methodologies that are coming out lately. I mean, they've been around for a while, but the Fourier transform here utilizes a large window of about 8 minutes. So that prohibits more granular analysis. This might explain why it may not correlate that well with the staging that you get from the sleep epochs, because the sleep epochs is about 30 seconds. Fourier transform also doesn't do terribly well with non-sinusoidal waveforms. For example, the phase A episode during CAP happens at an instantaneous time. Obviously, it lasts about 15 seconds or so, but then you have a lag period about that. And so that waveform is not necessarily sinusoidal. And so the Fourier transform doesn't necessarily do all that well for that. The phase coherence that I talked about compares the phase differences across 3 sub-windows. So again, that's just 3 sub-windows, not that great in granularity. The CPC also doesn't do necessarily a great job at distinguishing between REM versus wake. And it's not applicable with patients with arrhythmias, those with excessive ectopic beats, AFib, or paced rhythms. The other challenge is that the traditional method used EKG, but how do you extract respiration using a watch, which uses PPG? And there's probably various methods for that. One of the things is that during PPG, you have respiratory modulation of that PPG. There's a baseline wandering. There's the amplitude modulation, so the difference between the peak and the nadir, which also changes, and also the pulse width between the two. So there are a number of ways that you can extract respiration using PPG, but it's not something that necessarily has been studied broadly. I would guess that that's what's being used by Sleep Image, because this is the sort of figure that they have on the website, which kind of indicates that that's how they extract respiration.